afternoon, everyone. I'm Mahshid. I'm from RISE, Research Institute of Sweden, and today I'm going to present how we use the machine intelligence and the autonomous system to guide the performance testing towards reduction of the dependency on the models, source codes, and other artifacts, while preserving the efficiency of the activity. So, well, performance is one of the quality characteristics in the software quality model, which is of great importance to be verified specifically for the performance critical systems. It describes the time and the resource-bound aspects of a system behavior. And also we can summarize that performance analysis or performance evaluation is conducted to estimate or measure the intended performance metric for the software under the test or for the intended software system, detect some types of the functional problems which appear under certain performance-related conditions like heavy workload, and also detect the violations of the performance-related requirements. So, then the stress testing as a sort of or relevant activity to performance testing implies applying extreme or stress test conditions to the software under the test to accomplish the objectives of the performance evaluation. Some of the common approaches for generating the test, the stress test conditions are based on the source code analysis using evolutionary algorithms, based on the system models, like performance models, UML models, and also even using the use case-based design approaches. But we know that relying on the source code, system models, and those artifacts raises some issues of the limitations upon unavailability of those artifacts. And also, drawing a kind of precise or accurate performance model of a complex software system is a difficult task. Here is the point where a good motivation can show up for thinking about a model-free learning-based technique. And so among the learning-based or model-free learning-based techniques, we can say that model-free reinforcement learning is a machine learning technique which enables the learner or the smart agent explore the environment, learn the optimal policy to achieve the target without having a pre-knowledge or without having a model of the system. The learner can store the learned policy, and then it can reuse and replay the learned policy in the further similar situations. This is a very good advantage which leads to improvement in the efficiency of the agents by reducing the required effort of the learner in the similar situations. So we use this point, and so we tried to propose a kind of model-free reinforcement learning stress testing framework. In general, it's a stress test case generator to find the performance breaking point of the system. It's autonomous. Why? Because it's able to learn the policy, and also it's able to replay the learned policy without having a performance model of the system. And so actually we developed two types, or perhaps two variants of this smart framework. The first one was based on the simple RL, Q-learning as a well-known algorithm in the model-free RL domain, plus using the multi-experience basis. It was actually our heuristic. And then in the second generation, or in the second type, which was a bit more advanced, we used the fuzzy RL plus adaptive strategy selection. It was a kind of metadata feature which added to our smart agent. We called it SOFREL, Self-Adaptive Fuzzy Reinforcement Learning Based Stress Testing Framework. Actually, Both types, in general, have two phases of learning, or assume two phases of learning, initial learning and transfer learning. The learned policy is learned initially in the initial learning phase, and then it will be reused during the transfer learning. And so regarding the applicability, the most important part, we can claim that, okay, both of them are intended to reduce the dependency on the system models, including the performance model, and also source code and other relevant artifacts. And so we did several experimental analyses. We simulated one testbed environment, and so we did analysis for evaluating the efficacy in terms of efficiency and adaptivity of our solutions. According to our results, we can say that, okay, this framework, it can work very well specifically for the evolving variants of software system in the CI/CD process, and also software variants in the software product lines. And because we can say that, okay, the evolving variants and also software variants are sort of homogeneous or more or less similar variants of software system. And so according to our experimental results, this framework worked very well for those application points. Actually, that was it. And thank you very much for listening to my presentation. Feel free to share your feedbacks, ask questions.
Okay.
Thank you. Mahshid.